Alrighty guys, we're going to go ahead and take a look at our work problem over here. It says a person pushes a 20 kilogram box, so here's the mass of our box, to the right 5 meters, so this is talking about displacement, how far it's moving, with a force of 43 newtons across the gravel. So since the person is pushing this box, that means that we have a force applied happening here. The coefficient of friction between the box and the floor is 0.21. Coefficient of friction is mu. And the first thing it wants us to do is figure out force applied is doing work by transferring energy from what to what. So anytime we're talking about a person, we're talking about the person's energy. And a person's energy comes from chemical energy. So they are transferring from chemical into, well, what is the box doing when they push it? It's moving. Because it's moving, it's transferring chemical into kinetic. Next, we want to figure out the work done by the force applied. And if we look up here, it's kind of labeled for us already on our diagram, but I'm going to start putting our numbers in here. So from here to here is our displacement, which we said was 5 meters. And if we look at our box, we are applying a force in the same direction that it's moving, and that force is 43 newtons. So if we want to find out the work done by force applied, well, all we have to do is use our work equation. We know work is equal to force. In this case, that's force applied. So that's 43 newtons times our displacement. Our displacement is how far the box is moving. That's 5 meters times cosine theta. And theta, just a reminder, is the angle between the force and the displacement. So force acts in this direction and displacement acts in the same direction. So the angle here is just 0. Cosine of 0 is just 1. So if we multiply all this through and solve, we find out that the work should be about 215 joules. Go ahead and put that right here. Next, the friction on the block is doing work by transferring energy from blank to blank. So when we're talking about friction, friction is always acting in the opposite direction of motion. So friction in our diagram is going to point in this direction, and we know that displacement points in that direction. So what does that mean? Well, since friction's acting in the opposite direction of motion, it's always taking energy out of kinetic. So it's transferring energy from kinetic into thermal energy. And thermal energy is just used to slow down objects. It's another fancy way of just saying energy that we quote unquote lost during this process. So the work done by friction, well, we have to do the same thing. Let's set up our equation. Work is equal to our force, in this case, is force friction. Our displacement is still 5 because it's still that 5 meters that it's acting over. And then cosine theta, well, we see that friction is pointing to the left and displacement is pointing to the right. So the angle between these two, since they're in opposite directions, is 180. We don't know what force friction is right away because we see in the problem that we're just given the coefficient of friction, but we can solve for that. We have up here the equation, force friction equals mu times force normal. Since this box is on a flat surface, force normal is just equal to force gravity, which just means that it's equal to mass times gravity. So we get force friction equals mg times mu. And again, mu is right here, our mass is right here, and g, we know, is just 9.8 because that's gravity and it's on Earth. So we plug all that in, and we find out that the work done by friction in this problem should be negative 205.8. And work that is done by friction will always be negative because friction always acts in the opposite direction of motion. Another way I knew it was negative is because my cosine 180 here is equal to negative 1. So that means that the work done by friction will always be negative if, and this is always the case though, but if the displacement of our object is in the opposite direction of the force, just like here. Force points to the left, displacement points to the right. Now that we solve for work from the force applied and work done by friction, we need to figure out the velocity of the block after it's being pushed. And when we think about velocity, that's really telling us that we need to think about kinetic energy. And that just means that we have to figure out what kinetic energy is. Well, if we look at what we already did here, we figured out that force applied is transferring 215 joules of energy into kinetic. So here's our kinetic here. But simultaneously, force friction is taking out 205.8 joules of energy. So what does that mean? That means that whatever energy is left over is going to be our kinetic. So all we have to do is just add our works up. So if we add up the work, we find out that our kinetic energy should just be 9.2. I'm just rounding here, but let's say 9.2 joules. Once we figure out the kinetic energy, it's just a piece of cake from here. All we have to do is write our kinetic energy equation, because we know kinetic energy is equal to 1/2 mv squared, and we can solve for velocity. So let's manipulate this equation to solve for velocity. So we get 2 times ke divided by mass square rooted is equal to velocity. Plug in our numbers and we find out that the velocity should be 0.96.